A 60-pound boulder is suspended over a roof by a 40-foot cable that weighs 10 pounds per foot. How much work is required to raise the boulder with the cable up to the roof? Okay, so they didn't give us any dimensions on the boulder, so we're going to assume it's just like a point in space. So work done on the boulder is force times distance. Force is the weight, so that's going to be 60 pounds, times the distance that you have to move that boulder, which is 40 feet. So my work is 2,400 foot-pounds. So that's just the work that's done on the boulder, but there's also some work you have to do to pull up this chain, because that's a pretty heavy-duty chain. It's 10 pounds per foot times 40 feet. You might think you could just do 10 times 40 to figure out how much it weighs and then calculate the work done. But you can't do that because each piece of the cable requires a different amount of work to pull it up. Like the stuff that's almost already on the roof takes almost no work at all, whereas the piece at the bottom requires a lot of work. So what we're going to do is we're going to take this chain, this cable, draw a picture of it. Here's 0 feet from the roof, and down here 40 feet from the roof. So this piece right here doesn't have to move at all, and this point right here has to move 40 feet. Pick a random spot along the cable, call it X, and we're going to make a tiny little chunk here, delta X. And I want to figure out how much work it takes to move this tiny little slice of chain up to the top of the roof. So the work done on a tiny little slice of the cable is also force times distance. Force is 10 pounds per foot times delta X 8. So that will tell me how much that little slice weighs, right? So for the boulder, we used the 60 pounds as the force. For the slice, I need to know how much that little slice weighs. So this is force. 10 pounds per foot times delta X feet. And then distance is X. It has to move X feet up to the roof. So just to simplify, this is 10x delta X. So then I have to add up the work done on like all these tiny little slices along the cable. So my total work is going to be a sum from I equals 1 to n, where I add up the work done on all these slices. So I have 10 xi delta x. So I have not just this one generic slice, but this is x, I don't know, 10. This one would be x11, x12. So I have to add up all these the work done on all these slices xi. And then I take the limit as n goes to infinity. This translates to an integral. And it's going to be the integral of 10x dx. And my bounds of integration are the smallest distance that has to be that the cable has to move to the largest distance, 40. 0 to 40. All right, so that is 5x squared, evaluated from 0 to 40, which is 8,000 foot-pounds. And then my total work is the work done on the boulder plus the work done on the cable. So 2,400 plus 8,000 is 10,400 foot-pounds.